Our planet, a delicate, living sphere, blue-green, suspended in the vast darkness of space. For millennia it has nurtured life in all its breathtaking diversity, but this precious equilibrium is now under threat, a profound change driven by a single species, us. Human population has swelled, and with it, an insatiable appetite for energy. Our cities glitter through the night, our industries churn relentlessly, and our journeys span continents in mere hours. This progress has a cost. Every lump of coal burned, every gallon of fuel consumed, releases carbon dioxide, an invisible blanket trapping the sun's heat. This is the mechanism of global warming, not a distant forecast but a present, often brutal reality. The great ice sheets are retreating, glaciers melt, their lifeblood swelling the oceans. Landscapes are parched, forests become tinderboxes, and wildfires rage across continents. Elsewhere the skies open with fury. Floods inundate towns, destroy homes, and wash away the soil that sustains us. Our finely balanced world is being pushed to its limits. The rhythm of nature is disrupted. This crisis demands not just our attention but our ingenuity. We must look to science, to innovation, and to the remarkable world of chemistry for new answers. We must find a way to mend the atmospheric blanket we have woven before the damage becomes irreversible. In our search for solutions, we sometimes find them in the most unexpected of places. Here, we turn to the molecular world, intricate structures, powerful forces invisible to the naked eye. Within this realm we find ionic liquids, salts that are liquid below 100 degrees Celsius. At first glance it seems a contradiction. We learn salts are crystalline solids, rigid and brittle, requiring immense heat to melt, not liquid. But ionic liquids are composed of large, bulky, asymmetrical ions, cations and anions that do not pack neatly into a crystal lattice. This awkward packing prevents easy solidification, keeping them liquid far below 100 degrees, often at room temperature. They have extremely low volatility, virtually no vapor pressure, so they do not release harmful fumes. They are thermally robust, withstanding high temperatures without breaking down, crucial for industry. Most exciting is tunability. By choosing cations and anions, scientists design specific properties for specific tasks, a near-infinite chemical playground. We can create ionic liquids to capture CO2, dissolve materials, or catalyze reactions, silent architects of cleaner chemistry. So, how can these remarkable liquid salts help us tackle excess CO2? They act as effective carbon traps, selectively capturing CO2 from mixed gases like flue gas. This happens in two main ways: physical absorption. Like a room lined with a sticky sponge, CO2 sticks via weak intermolecular forces and can be released by changing pressure or temperature, then the liquid is reused. Chemical absorption is a lock and key. Functional groups, for example amines, form temporary chemical bonds with CO2. It is more selective and higher capacity but needs heat to reverse, releasing a pure stream and regenerating the ionic liquid. The beauty is choosing the right tool: gentle, low-energy physical absorption, or strong selective chemical absorption for dilute streams. This adaptability places ionic liquids at the forefront of carbon capture technology. As global emissions continue, scalable, selective, and recyclable solvents become essential pillars of mitigation. The field of ionic liquids is not standing still. Task-specific ionic liquids, molecules designed from the ground up with functional groups that enhance CO2 affinity. Hybrid systems merge ILs with metal organic frameworks or zeolites, creating supported ionic liquid phases, CLPs, solid-like carbon sponges with liquid selectivity and reduced viscosity issues. Ionic liquid membranes made by polymerizing ILs or embedding them in polymers enable continuous, energy-efficient separations. At fossil fuel power stations, flue gas is channeled into absorption columns where ILs selectively scrub CO2, then regenerate to deliver a pure CO2 stream for storage or utilization. In natural gas processing, ILs remove CO2 and acidic gases, purifying to pipeline standards while avoiding volatile hazardous solvents. For day C, fans draw ambient air across reactive IL contactors. Even at just over 400 ppm, specially designed ILs can capture CO2, one molecule at a time. What began as curiosity now enters pilots and industrial retrofits, the front lines of decarbonization. These advances are transforming carbon capture from theory into practical, scalable engineering. Challenges remain: high cost, viscosity, and industrial scale-up. Responses include cheaper synthesis, solvent recycling for thousands of cycles, lower viscosity formulations, and improved contactors to shorten gas travel distances. Scaling requires massive plants, investment, and bold policy, a worldwide commitment to clean industry. We stand at a pivotal moment. Ionic liquids will not save our planet on their own, but they offer a tangible way to cut emissions and help rebalance our atmosphere, a vital piece of a larger net zero puzzle. With science and engineering, we can decouple progress from pollution and begin to heal the Earth.